Facebook ya. Oke, start, silakan Pak Haryo.
Baik, Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi Bapak dan Ibu sekalian. Terima kasih atas kehadiran Anda semua pada kurikulum fisika daring Pusat Penelitian Fisika LIPI. Saya Suharyo Sumawidagdo hari ini bertindak sebagai pembawa acara serta moderator kolokium hari ini. Sebagai informasi, kolokium fisika rutin diselenggarakan setiap hari Selasa pada pukul 10.30 sampai 12 WIB dengan menghadirkan pembicara dari internal Pusat Penelitian Fisika LIPI maupun pembicara tamu dari luar LIPI. Topik yang disajikan sangat beragam dari fisika partikel, fisika material, fisika optik, fisika instrumentasi, hingga fisika bumi, dan mencakup juga tutorial serta sharing pengalaman penelitian dan sekolah di luar negeri. Insya Allah kita akan rutin terus menyelenggarakan kolokium ini hingga setidaknya akhir tahun 2020. Hari ini kita menghadirkan pembicara tamu dari Pukyong National University, Korea Selatan, yakni Dr. Parada Hutauruk. Saya bacakan dulu sekilas profilnya. Jadi, Dr. Parada Hutauruk menyelesaikan pendidikan sarjana di jurusan Fisika Institut Pertanian Bogor, kemudian Magister Fisika di jurusan Fisika Universitas Indonesia, dan S3 Ph.D. di University of Adelaide, Australia. Sejak bulan Juli tahun 2016 hingga Juli 2020, Dr. Parada bekerja sebagai peneliti di Asia Pacific Center for Theoretical Physics di Korea Selatan. Dan baru-baru ini dari Agustus 2020, Dr. Parada menjadi Research Assistant Professor di Pukyong National University, Korea Selatan. Dr. Parada berpengalaman dalam berbagai penelitian seputar fisika teori fisika nuklir dan partikel elementer dari kuark, neutron, dan sejenisnya. Pada kolokium kali ini, Dr. Parada akan membawakan presentasi berjudul How do we understand the internal structure of hadrons from a quark-gluon degree of freedom perspective? Nah, baik Pak Parada, bisa silakan share screen dari sekarang. Waktu yang dialokasikan untuk presentasi sekitar 1 jam. Setelah presentasi sekitar pukul 11.30 kita akan membuka tanya jawab. Nah, saat tanya jawab atau menjelang waktu tanya jawab, kami membebaskan Bapak Ibu untuk menulis chat pertanyaan dengan bertanggung jawab. Silakan juga jika mau bertanya melalui audio dan menampilkan video dengan terlebih dahulu meminta izin melalui chat. Nah, untuk Pak Parada, kalau ada chat pertanyaan yang masuk di tengah presentasi bisa diabaikan dulu karena kita akan kumpulkan dulu dan kita bacakan saat sesi tanya jawab. Nah, baik, sekarang bisa mulai presentasinya.
Oke. Wait a second. Wait, I get a problem. Oke. Oh, ini agak susah. Gimana ya? Saya nggak bisa share screen.
Terlihat kok, Pak. Bisa dibuat ini saja di full tadi tampilan PDF-nya. Ya, ininya saja di maximize, Pak. Dibuat maximize.
Nggak mau ya? Oke.
Jadi view-nya itu kan yang 125% dibuat maximize.
Oh, sorry. Oke. Udah ya, kelihatan ya?
Ya, clear.
Oke, terima kasih Pak Haryo atas perkenalannya. Saya mengucap terima kasih atas undangan yang diberikan. pada kolokium saat ini saya akan berbicara. Sebelumnya saya perkenalkan nama saya. Nama saya Parada Hutauruk. Saya bekerja di Nuclear dan Hadrons Theory Group, Departemen Physics, Pukyong National University. And the topic yang saya akan bicarakan pada saat ini adalah mengenai how do we understand the internal structure of the hadron from the quark-gluon degree of freedom perspective. The outline of my talk is I will start. Sorry, nggak apa-apa bahasa Inggris ya?
Ya, nggak apa-apa, Pak. Campur-campur boleh. Oke. Tidak ada batasan. Asal jangan bahasa Korea ya.
Enggak. Okay. I start with the introduction, and then I will explain about the quark and the meson in the Bethe-Salpeter equation, NGL model. And then I will talk about the gap equation, how we write, how we got the gap equations, and also Bethe-Salpeter equations. And the next, I will talk about the pseudo-scalar meson structure, which is has a simple structure. And then I will show you how to get the pattern distribution function of the pion and the kaon, also the form factor. And then the next, I will also talk about the light vector meson structure. The same like this structure of the vector meson is almost the same like a pseudo-scalar meson, but has a different spin. But they, of course, they have a different structure. And also I will show you pattern distribution function and transfer momentum distribution. And at the end of my talk, I will try to summarize of my talk. Okay, let's start with I will bring you to high school study, which is this about the history of atomic model. At the time, we don't understand what is the atomic models. And then Democritus in 40, 60 before century suggested the how we understand the structure of the atomic. And then after that one, many scientists like John Dalton, G.G. Thomson, and Niels Bohr, and also Ernest Rutherford, and also Erwin Schrödinger suggested the atomic model, which is I will explain later in more detail. And the important things from the history is James Chadwick is discovered the neutron in 1932. So this kind of the model that suggested by John Dalton, which is the model like this one, the atomic model makes some like a hardcore sphere like this one. And then Thomson also 1897 suggested there is a positive negative charge inside the atomic, right? And then Rutherford also suggested the model what he calls there's a nucleus inside the atomic model, the atomics. And also Bohr suggested like this one, as we know, in 1913, there is a nucleus, but also there's energy levels here. And Schrödinger also in 1926, he suggested like model, he call it the electron cloud model. But from this, every suggested is to get a Nobel Prize every year. Dalton, Thomson, and Rutherford get a Nobel Prize for their atomic model. And then interesting things is when Chadwick founded the neutron. Why is very interesting? Because we know that atomic is not like a empty space, but it has a structure. It's not a point particle, but there's a structure based on the neutron and proton. And now we know that atoms have a structure where the atom made up by negative and positive charge particles. Also now we know that atom is not a point particles and not smallest particle anymore after Chadwick discovered neutron. And I will bring you this James Chadwick setup in 1932, how he discovered neutron. This very simple, a simple experiment, which is the source of the plutonium, you can see here, which is a produced alpha particle with the energy 5.7 MeV, hitting the beryllium target here, and then to yield the free neutrons here, and then it collides elastic with the proton in the hydrogens, which are rich paraffin, and then these protons detected in the detector. If you want to see this, I think you can search it in Google too. And then but more specific, you can find in this reference, Physics Today 66, 2013. And then we know that atomic now consists of the proton and neutrons. Also, proton discovered in 1919, and neutron discovered, as I mentioned before, is in 1932. In the late 90s, we already detected the radius of the proton was around 1 Fermi, which is 10 minus 15 meter. So this is pretty interesting. After we found the proton and neutron, and then we can describe all the nuclear interaction in terms of the neutron and proton. You can see here proton and neutron and interaction, and the neutron, which is this actually pi zero, not pi plus, pi zero is a neutron to proton. And then I can say that the nuclear interaction can be explained in the nuclear level at this time, okay, when we found the proton and neutron. And then also is more interesting is after we found the neutron and proton, we can make a predict table, which is this number of the protons, different number of the neutrons, and then the atom has a different properties. There's a stable, unstable, and the other. If you increase the number of the proton and the neutron, and then the atom is properties are different. So we then at the time after we found the proton and neutron, and then we can explain more, the interaction of the nuclear or atomics interaction. But we actually is not discover only proton and neutron, but we discover so many particles in the experiment. It's like a pi zero meson, K mesons is this sigma is a baryon. So a bunch of the particles we can find it in every year. You can see here, and then this we call it a particle zoo. Okay, so because so many particles, and then the question is how do we understand these particles and their properties? Is it possible to classify them based on their properties? This I want to answer. Wait a second. Okay. Oke. Udah kelihatan ya?
Ya, bisa dimulai kembali. Ya, Mai ya.
Okay, sorry for the mistake. My battery is off, and then it's just go. Okay, I will continue as a particle G that way I will explain earlier. And then how do we understand this particle and their properties? Is it possible to classify them based on their properties? And then this the question we should ask is, are neutron and proton fundamental particles? And then let's hold this after the next story. So there's a new interesting thing after the neutron and proton found it. And then there's a quark proposal from Gelman and Zwick that he call it eightfold way. And in this formula, Gelman and Nizima, which is actually at the time, Nizima tried to include the strings stringness. And then if there's a charge and isospin relationship that we call this one, this charge with the unit electronic charge, and this the isospin with a jet component, and then this baryon number and this stringness. And then the stringness and the baryon, you can sum up, become a high-force charge. You can see here. And then all the particles you can classify based on the the isospin in the jet component and then the stringness. And then you have a kaon here based on the charge. You can see pi minus made up by d quark and anti u up quark, and the string quark anti up quark k minus. And then these have a charge -1. Okay, and then we could just neutral charge. It can k0, eta 0. And the other you can classify like this one, and then key plus based on made up by u quark and string quark, anti-string quark, and then this pi plus, which are u quark with the anti-d quark. So with the charge is a pi plus, charge is a plus. And then you can also this for the isospin 0. and then parity minus. And then if you increase the spin, which is a spin 1 and the parity minus, and then you can classify also that you factor mesons. So you can factor minus meson with the parity minus. And also you can baryon this D meson, which is you include the heavy quark, which is like a charm quark, and then this 1 minus meson, which is there is a charm D0, D star, and then the others also. And then also you can classify the baryons, which are charm with the charm quark, the heavy baryons, and the 3 plus baryon. So using this formula, and then by quark proposal by Gilman and Zwick, and then you can classify all the particles, which is you can see here based on this the structure. And then from the experimental side, like a Stanford Linear Accelerator, MIT elastic scattering, they use electron-proton elastic scattering. They provided first evidence for the quark. This is the discovery of the quark. This actually, the quark is founded in 1969, but there's some debate at the time, which is the first time quark discovered is in 1968 until 1972. They're using the high energy electron beams. And then at the end, the final state, they only detected the electron. You can see here in the Physics 7, 2014. This is the actually this is the accelerator. This is a magnet maybe, yeah. And then this the slot. And then the question is, what happened after the quark discovered? Let's continue our story. And then we know we can answer are the proton neutron fundamental particles? Of course not, because we already found the quark, and the quark become a building block of the matter. You can see here there is a 6 quark, up, down, charm string, and top bottom quark. And there's a lepton, which is a fundamental particle also, electron, muon, tau, and then neutrino electron, neutrino muon, neutrino tau. These particles can be, interact with the, in the strong charge, in the strong interaction, there's a gluon as a carry particles carry gluon, and then in electromagnetic you can this gamma, and then in weak interaction you can use it the Z and W plus minus boson. So now with this building block of the matter, all the matter in universe should be able to describe in terms of these quark or gluon in the strong force, in the strong interactions, right? And then, but however, we should keep in mind by using quark-gluon, it doesn't mean that all previous knowledge of particle and interaction based on the nuclear level are not correct. So this not you should keep it in mind. And then our knowledge on particle and their dynamics and interaction in nuclear level is help us to guide our obtained result in terms of gluon, quark-gluon level. So they are complementary. So if you want to look at this one and then you want to write the interaction, all the interaction between these all quarks and lepton using these intermediate particles, and then you can write down Lagrangian, that you call it Lagrangian for the standard model of particle physics. And then if you want to look at the strong interaction, which is there's a gluon carry strong force, and then you can write like this one. And then if you want to describe more interactions, and then you can include the weak interactions and also Higgs boson interactions, and then it's more complicated equation. And then if you want to more, you including the other particles like a Higgs field and the others, and then you can get an additional Lagrangian. And then if you want to include the Higgs ghost, like a virtual artifact, like a Higgs from the Higgs field, and then you can get this one. Okay, so more complicated again, you can include like more ghosts into Lagrangian, and then you can get the Lagrangian in the standard model more complicated. But if you look at this one, and then this all that Lagrangian, it can sum up like this one, and then it will be fit in the 1 mark. It means that it's not really complicated. Okay, you can satisfy by like this one. You can write Lagrangian like this one. But my focus is not all the Lagrangian, but part of them, which is we focus on quantum chromodynamics, which is a strong interaction. So this keep in mind also. I will talk about this strong interaction, which is we talk about the hadron structure. And then the other important thing is particle size. If you were talking about the hadron structure and then QCD, which is we focus interaction quark inside the proton meson with scale 1 Fermi, which is I already mentioned earlier, which is we already found the proton has a size like a 1 Fermi. So, but if you look at this, the size for from starting from the atoms, this atom has a 10 minus 8 centimeters, and if you go deeper into the nucleus, and you can get 10 minus 12 centimeters. And if you look at the size of the nucleon, and then 10 is the size is like 1 Fermi. This 10 minus 15 meters, or you can say 10 minus 13 centimeters. And the quark, if you look at the quark also, this quark has a size the same like in the nucleon, right? So the diameter of the nuclear quark you can see in the size. So the point is we will talking about the scale with 1 Fermi, with which is the scale of the nucleon or hadrons. Okay, so before we go to that one, and what is quantum chromodynamics? What is the properties? Let's continue. So QCD, as we know, is a fundamental theory for the strong interaction, as I already mentioned earlier, and then which is a quark and gluon basic degree of freedoms. And QCD is a non-abelian gauge theory, which is the operator is a non-commutative, and where the dynamics are governed by this Lagrangian, this kinetics part, and this the electromagnetic the gluon part. Is you can see here this we call it tensor field, and this different covariant derivative, and then you can define like this one. Most important is there's a gluon self-interaction have many consequences. This one, okay. This a gluon interact between the gluon, and then as we know that QCD start with almost massless quark and massless gluon and gauge boson, but their interaction generate mass of the hadrons more than 95%. So this is really important to know about this how they generate mass. Okay, these the properties of the QCD. If you look at the short distance scales, which is in this scale 10 minus 16 to here, and you can see here in the large momentum in the here in this region, QCD has a the interaction between quark and gluon is become become small logarithmically. Okay, you can see here it's become small. That we call it a perturbative QCD regime. This well done with the asymptotic freedom, which is a gross Pulitzer and Wilczek get a Nobel Prize 2014. And the other one you should keep in mind that hadron structure and QCD have two emergent properties. You call it confinement, and then dynamical symmetry, chiral symmetry breaking, or you call it DCSB. And in the low energy limit, in this here, and then momentum square below 1 GeV in this area, and then at large distance scale, which is larger than 1 Fermi, which is this 1 Fermi, and then you got a 1 Fermi, and then in this area. And then QCD is governed by quark color confinement, you call it, and dynamical chiral symmetry breaking, DCSB, which is this, you call it non-perturbative QCD regime. And all hadrons are chiral shielded, which is mean that you just only found the hadrons, not quark, right? So even that quark has a color, quark and gluons has a color, and then you just only see the baryons and meson. which is made up by this one. Okay, these two the properties of the QCD, which is a confinement and the dynamical chiral symmetry breaking. And after we know the properties of the QCD, and then now we calculate the hadron structure using QCD. Let's continue. And before that one, I will give you some introduction that you ask the question, is it possible to calculate the structure of the hadron directly from the QCD? The answer is unfortunately, the QCD as underlying theory as a strong interaction, as we know, is unable to directly predict structure of the hadrons. Okay, so what is the solutions? The solution is you can use lattice QCD. This is a popular technique to calculate structure of the hadron PDA or general pattern distribution using large momentum effective theory. Because this colloquium I didn't explain more technically here, and then you can go to this paper if you want interesting to learn about the last momentum effective theory. And then the other thing is a chiral perturbation theory, where the interaction based on the pion field. This you can use it. And then the other is a QCD inspired model. This inspired model mean mimicking feature of the QCD, which is a feature is a confinement and the CSB. This model, you can say like a Nambu-Jones-Lasiano model and Dyson-Swinger equation model, QCD sum rules, instanton model, covariant non-local chiral quark model. This model is a QCD inspired model. So, but in this talk, I will focus to this very simple model. We call it Nambu-Jones-Lasiano model. I will explain later more detail about this model. And then this, I will just took it from the Hubbard slide. This is an electron-ion collider meeting 2018. All this QCD inspired model has been used to, to explain the data from the Jefferson lab. So this is our model, which is the pink one, and then you can see the other model here. And then also you can use the lattice QCD result like this one to calculate this. You calculate like the pion for the pion against the momentum square. This the pion form factor with the momentum transfer square. And then after we know lattice QCD and the other model, we can put to understand what quantities do we compute to understand the hadron structure. So to understand the hadron structure, we compute like a pattern distribution function, elastic form factor, fragmentation function, generalized pattern distribution function, and you call there's transfer momentum dependent or call it TMD, which are provide complementary information. Okay, these usually people calculated the cross section or differential cross section, but these all PDF or form factor, which is has a relationship to cross section. I will explain this more detail later. And from experimental side, experiment data, why we interesting is experimental data for hadron will be coming soon from Jefferson lab and GPark also, or CNS, CSPS in CERN, COMPASS, and future experiment electron collider. This will start it 2030, I think. So this the experiment that we will do in electron ion collider, I will just show you. I didn't explain this more detail, but I just show you this kind of interaction. Before computing PDF, electron form factor and form factor, what is hadron? We have to understand hadron is a subatomic composite particles made up by two or more quark held together by strong force. You can see here is a proton, up, down, and down, up, down, and up quark is a up, down, down quark. This neutron and the pi plus u d anti-quark, up quark and anti-quark, d anti-quark, and up quark is with the d quark. So if you spin, you can based on in terms of the spin of the quark, you can understand the spin of the how the spin of the proton with spin half come up, and then the charge will 1, right? So this you can understand the properties of the baryon and meson. I can say generally baryon are fermion with half integer spin, have odd number of quarks. Meson are boson with integer spin, have a number of the quarks. But in this talk, I will focus on meson, which is a simple structure. You can see also in Wikipedia. Okay, how do we construct meson in the quark model? So this I will show you meson in the base A NGL model. This is a meson, this is a baryon, but actually meson is not only consists of the 2 valence quark, but there's a gluon. Also the baryon, there's a gluon inside. So it's not very simple like a three quarks, but there is a gluon inside. This is a glue ball. Okay. Okay, meson in the NGL model. NGL model was invented by Yuichiro Nambu and Giovanni Gionalascidio in 1961. He was at University of Chicago at the time, and this model is inspired by BCS theory of superconductivity. Maybe people who working in the condensed matter know about this one, and was originally a theory of elementary nucleons, but this discovered again, NGL discovered again in 80s as effective quark theory. Number one held Nobel Prize for physics for discover of the mechanism of the spontaneous symmetry breaking in subatomic physics in 2008. Okay, this is the meson with NGL model. In this case, I show you. I will show you 3 flavor NGL model. This very simple model contain only 4 fermion interaction, which is this kinematic part, this interaction part, this quark field with the flavor component, with this the coupling constant, and this Gell-Mann lambda A, which is run from 1 to 8. We call it Gell-Mann matrix in flavor space, and this current quark mass. So this interaction, the Lagrangian for the NGL, I will just let you know if you think that this more technically, it just accept first, and then hopefully you can understand anyway. So you can see in this in our paper 2016 about the NGL model. And in the NGL model, gluon exchange is replaced by 4 fermion contact interaction by integrating out the gluon field and absorbed into the coupling. So it's just like this one. That's why you call it a quark effective theory, which is this gluon intermediate state can be reduced to this one. This is a coupling constant. So more simple without the gluon inside, but the gluon is absorbed to the coupling constant. So, but because NGL model is a 4 fermion contact interaction, so he has a lack of confinement, which is the properties of the QCD. It can be simply seen by the quark propagator has a pole, so there's a divergent. So to solve this problem, we use we have to regularize using the proper time regularization, you call it. This is to simulate confinement. About this one you can see in this paper. In the proper time regularization, what we do is this is a propagator 1 over this a propagator power n, and then you can translate to 1 over n minus 1. This one integrate to infinity, and then these are the d tau. There's new variable here, and then this is the propagator, and then you can see here there's no pole in the propagator. But to simulate confinement, we decided to use the cutoff, which is cutoff 0.24 GeV, which is a cutoff of lambda QCD. And then we can determine this one. Okay, I will, then we calculate the gap equations using the propagator. This is the propagator in the momentum space. And then you calculate the mass like this one based on the Feynman diagram, and then you get the mass, which is this. There is a chiral condensate as an order parameter of dynamical chiral symmetry breaking, and it's defined like this one. So what I want to show you here is this NGL model, which is mimicking all the properties of the QCD, where confinement and the CSB. Okay. So, and then by using the chiral condensate, and then you can generate mass by interaction with the vacuum one. We call it here. And then condensate is not equal 0. So if I saw the picture here in how the gap equations, this you can see this the coupling, which is show you the interaction between the quark in the system, and then this how they generate the mass. You can see here, if you take the chiral limit, you call it, if you set quark current quark mass equal 0, and then equal chiral limit, and then you can see the interaction, it start from here, and then from is where is the coupling constant G pi divided by G critical, which is generate the mass. And then if you take the current quark mass is not equal 0, for example 5 MeV, and then this show you the same patterns but how they generate the mass. And then if you increase more like increase like a 50 MeV, and then you can see this how they generate the mass from the vacuum one. Okay, but the NGL model is not momentum dependent. Momentum dependent, it means you can include the gluon, but in this case it is the other model, which is calculated using I already mentioned Dyson-Springer equation model, and then this mass generated by with the momentum. They include the gluon inside. So you can see here, if they set the current quark mass equal 0, a chiral limit, and then you can see the mass generated over the momentum, right? And then if you increase the current quark mass, and also the current quark mass increase over the momentum, and then you can get this one. So the NGL model can be used for low momentum P on low energy. This BSA NGL model, so dynamical symmetry breaking DSB that generate a mass, which is the same symmetry as a QCD has. More detail about this model you can see in the Roberts 2008, and you can see in our paper 2016. And these are already mentioned before, that the chiral limit, the constituent quark mass as a non-trivial solution, which is this is not equal to 0, and then the provide coupling larger than critical, right? And this we call it this golden phase, Nambu golden phase. If you and then this Nambu golden phase occurs when the chiral has been dynamically broken. And then the critical, you can formulate it like this one. And also you can see from the gap equation figure, this one, from this figure, you can see that the indicate which is the constant quark mass is not the same like a current quark mass, and then the chiral condensate is not equal to 0. This indicate dynamical mass generation, as I already mentioned. And then the chiral condensate at 0, you can find also in this part is chiral condensate equal 0, and then which is the G pi, the coupling constant is smaller than G critical. This well known with the Wiener Weyl phase. Okay, that's all in the NGL model, how we build the quark inside the NGL model. And now we asking the questions after that one, and how to maintain the bond state, because as I mentioned before, we cannot find the quark outside the hadrons because it's always singlet. Uh, and then I will explain how we perform like a beta salpeter equations to keep the bond state. And here, as we know, the beta salpeter equation for the pion and the kaon mentioned in the NGL model are quark and anti-quark bond states, which is a properties determined by BT salpeter equation. And then if you write the Feynman diagram, is like this one. Okay, these the interactions with the quark, pion with the quark, and then you can write like this one. And these point interactions. And then there's an interaction with the vacuum and like this one. And then you can write using the T matrix, you can given like this a kernel, the kernel here, and then you can integrate because this there is a loop here, there's an integral over this one, and then this a kernel, and the propagator, and then this a T matrix and the propagator. And then you can define the T matrix using the vertex, which is gamma 5 lambda, and is a gamma 5 lambda dagger. So you can get the T reduced matrix like this one. So okay, what I am showing you is from this pole you can determine the mass of the kaon, and the pion using this formula. And then this you call it bubble diagram, which is translated, it's not here, but it's the same like this one, okay? And then from that one, you can get the mass pion for the kaon formula like this, expressed like this one in proper time regularization. And then also you can calculate the coupling, Mason quark constant that we need to calculate the hadron structure. You calculate this one, this coupling constant for the pion, kaon, and rho meson, and the decay constant you can also calculate it like a pion and kaon, right? Expressed like this. This calculated in the proper time regularizations. I just want to show you. I didn't mention very detailed because in this colloquium, so I just show you the formula how to get the mass for the pion, kaon, and also decay constant, and also the coupling, right? So using that one, and then we can determine the coupling like this one. How we determine is we just using the mass of the pion, mass of fit to mass of the kaon and rho meson, and also pion decay constant, and then we can get this G pi 0 lambda UV and string quark constant quark mass as listed in here in the table, right? So we can this for the kaon, rho, omega, pi, key star, this kaon, this kaon, this quark condensate for the up quark, quark condensate for the string quark. Okay, now we go to the pattern distribution function, which is in the NGL model, and this picture is very interesting. If you look at this, imagine this hadron, and then hadron is boosting to this direction with the x direction, we call it this longitudinal directions, and then there's this transfer, which is a plane transfer plane, and then this transfer momentum and this longitudinal momentum, and then this the quark inside the hadrons. If you make a graph in 3D, and then you can get some like this one, this longitudinal one momentum, and this the transfer momentum, and then if you plot together, this looks like this one. And you can also look at the longitudinal one, which is interesting pattern distribution function. If you integrate, get the lambda equal close to 0, and then you get the pattern distribution function look like this one. So, and then you can also get the integrate the longitudinal momentum, and then you get the transfer one. So this picture is very interesting, which is show you how the quark momentum in longitudinal and transfer direction. The definition of the transfers and the longitudinal is the same like if you learn introduction physics, which is transfers like this one. If you shaking your hand, and then this rope will be like this one, right? The transfer momentum is like this one. And if you're shaking in the longitudinal way, and it's like this one. So this definition is almost the same like this. I mean, longitudinal momentum and the transfer momentum. And before we go there, and then I want to show you the deep elastic scattering, which is this a proton in this way, and this electron and goes that way, and this is the initial momentum, this final momentum. There's a transfer photon here, and then produce another particle, which is we don't know. And then the transfer momentum we can define like this one, as you see here. And this longitudinal momentum, which is come from the number of the quark, the quark in the protons, and then you can write down like this one. This okay, and what I want to show you is unpolarized differential cross section. You can write down this differential cross section. This the structure function. So this connected with the why we calculate the pattern distribution function, because this connected to the differential cross section. So this we define. Also, you can not only for the gamma, you can also for G boson or W boson exchange. You can calculate the same way. And then, as I already mentioned, the structural function we can define like a structural function we can define with the quark distribution. This anti-quark, this a quark, and for the U and D, you can calculate like this one. And the PDF is actually is a probability interpretation. Okay, how we find the quark inside the hadron. Okay, now we calculation in the angel model, but I don't want to talk about this more technically. I just show you how we calculate that one, and using the Feynman diagram, this one. Oh, I'll skip this one. Oh, sorry. Before go to that page, I will show you Feynman diagram for the pion and the kaon, which is there is a two, as we know, the pion as quark and anti-quark, and this you can imagine this quark and then this anti-quark, and this anti-quark hit by photon, and this you define the operator like this one, and then this operator you can define like this one, and this for U and D quark and string quark. So we calculated these two based on Feynman diagrams, and then we get the pattern distribution function. But before that one, I want to show you here, as we know that in the space-time coordinates P, you can define like a P0, Px, Py, and Pz. And in the light cone coordinate, this a light cone coordinate, you can see, maybe you can asking what is gamma plus, gamma k plus, and P plus. And then in the light cone coordinate, you can define like a P, like P0, Pz, and P perpendicular. And you can define also P plus, which is a combined P plus, you can define like a P0 plus Pz, and then P minus is a P0 minus Pz. Using this formula, you can see here the gamma plus is also similar defined, okay? And then using this for the Feynman diagram, two Feynman diagrams, and then you can translate it, you can get valence quark and anti-quark distribution in the pion and the kaon like this one, okay? It's the same way as before. You can go from this one, and then this is a pion, and then this propagator, the propagator, and then this is a vertex and the propagator. And then to evaluate this one, it doesn't mean when you translate that one, it doesn't mean you get the valence quark directly. You have to using the moments. Why using the moments? Because using the moment is like in the low end, it means you satisfy baryon number, some rules, and the others conservation rules. Okay, so that's why we use this one before we get this distribution. And then we can, using this one, and then we get the valence quark and antiquark in the kaon, like this for expression, and the antiquark, this expression, this for the kaon. But for the pion, you can also easy by using this one, obtain the pion place by string quark, changing string quark with the light quark, and the coupling you can change it with the pion. And then you can also, as you know, U quark in the pion is the same distribution with the anti-D quark in the pion. As I mentioned before, we should satisfy. Hello? Halo?
Ini udah pukul 11.35. Jadi mungkin kalau bisa 5 atau 10 menit lagi diselesaikan ya.
Okay, so these are satisfy this baryon number and momentum rules. Okay, so this analog for the kaon and the pion. And this the result, and you can see here, this longitudinal momentum, this the distribution. And if you can see here, the red one is a up quark in the pion and up quark in the kaon, and this is a string quark in the kaon. So if you can see this distribution function for the kaon and the pion. Okay, so I will skip this one because time. And then you can also calculate the PDF ratio, which is really important. We compare with the experiment, is the same way you can get that one. But I have to let you know, before you compare with the experiment, you have to evolve this one to next leading order, which is using DigiLab. This one, using the DigiLab to 16 GeV square. Okay, so this you can see this one, and then I will jump some little bit because of time. And the moment PDFs for the X quark, you can write down like this one, this S quark in the kaon for every moment. So this 1, 2, 3, and 5, 5, 6. Okay, which is evolved to different number of the DigiLab number. And this for U quark in the kaon. And this I will jump it, this one, because I have 10 minutes, okay. This is a form factor of the pion and the kaon. This is a form factor. You can write the same Feynman diagram as a pattern distribution function. This for the quark and an anti-quark. And then you can write down this, the form factor is this matrix element, electromagnetic current for pseudo-scalar meson. And then from here, you can extract the pion form factor, which is, you can interpret it, the two Feynman diagram using, it's the same like a Parton distribution function, but the vertex is used is a gamma mu, which is a bare one. But this is not really correct. If you compare the experiment, you have to modify, you have to, oh, why stop? Sorry. Oh, well, I can move. You calculate like the same like a Parton distribution function. What happened? Okay, this form factor for the kaon compared to experiment. Okay, I will show you this the form factor of the kaon times the key square, and then you can get like this for graph, which is this one. The red one is a total form factor for the kaon against the momentum transfer. I will skip this one and skip this one. Okay, I will go to vector meson in the NGL model, and then vector meson, as you know, the vector meson, you can also has a spin 1 and parity minus. And then we focus to the rho meson plus, which is U and D, which is the same like a pion, right? But the mass is different. Mass is different, 70 MeV. This is the properties of the vector meson. I will focus to omega meson, pi meson, and also rho meson, right? 3 meson. I will show you the distribution function for that one. And the light vector meson is very interesting. We believe the mass of the depend on the constant quantum mass, right? So the mass of the kaon is larger than the pion, but that's because they have a string quark here. But however, it is not happen for the rho meson, which is rho meson has the same structure as the pion, but the mass is larger than the pion. So what is the this is cause? This because the difference of the quark spin orientation, which is spin-spin interaction. And you can formula like this one as of the quark is or the pion is a S1 quark and anti-quark, and you can write that like this one. For the vector meson, you can have like 1 times H2 is 4, and the pseudo-scalar is minus 34, minus 34. This is because the difference of spin. So that's why the mass of difference, right? And then because the structure of the rho meson and the pion is the same, and then you calculate the same way as a pion, but the vertex is different. Here is a 0 and 0. And then for calculate this one using the gamma plus, which is I focus on. And then you can write the operator like this one, gamma plus delta x minus this longitudinal to conserve the momentum. And then you can write down the distribution like this based on the these two diagrams, Feynman diagrams. And then finally you can get a distribution of the vector meson. It's like this one. Okay, I will just show you. And then the picture is the same for the rho meson. This model scale in the angel model, if you want to evolve, if you want to get this one compared to experiment, you have to evolve with the DigiLab. You can see in this paper about this DigiLab and these results. This for the unpolarized photon. This distribution of parton distribution function for the vector meson or PDF. Okay, so you can see like here, and then if you evolve to 5 square, and then you can show like this one. These are longitudinal momentum, and then you can show, you can see here the peak of the longitudinal momentum is around this one. And then this for the rho meson is the same like before. And now I show you for the omega meson. Is the omega meson is a peak is around here. This is a model scale. This after you evolve to g square 5 at gv square, and then you can find almost the same like a rho meson. And then if you look at the key star, which is a U S star meson, the quark, the constituent, the composite of the quark is a U and S bar, right? Because there's a S quark is a shifted little bit to here. And then if you evolve, this model calculations, model scale. If you evolve to key square 5 and GV square, and then you can get this one. It's also shifted if you compare to the rho meson. And then for 5 meson, which is 5 meson is a S bar, a string quark, and then you can see the peak is more higher compared to the rho meson. So if you evolve, also is the same like this one, but the peak is higher than a rho meson and omega meson, because this composed of the pi meson is a SS bar string quark, right? Which is the mass of the string quark larger than up quark. And there's this one for, if you see the distribution 3 dimension for this one for the unpolarized parton distribution function, which is the same like a parton distribution function. this for helicity, this for the transversity. Okay, you can see here how this longitudinal, this transfer momentum. So if you plot that one, and then you got like this one. Okay. So you understand now. You can understand how the the quark inside the hadron, for this case in rho meson, how they in the dynamics in the longitudinal momentum and the transfer momentum. And then this for the longitudinal, and this transversity in transverse of the rho meson. You can see here, which is this one, the longitudinal, which is go to opposite side with the transfer one. Okay, so you can see dynamics of the quark momentum inside the rho meson in terms of the KT's momentum transfer and longitudinal. Okay, and this one you can see also. I will show you like this longitudinal distribution and longitudinal transfer distribution and transfer distribution function. So you can see here how the dynamics of the FLL, you call it this one, over the key transfer momentum and
Baiknya Parada ini
the
11.45.
hadron structure.
Ini sudah pukul 11.45
Okay,
ya.
I'll finish. I need 11.45. Okay, I'll finish. Thank you very much. Okay, I will finish. I will leave the summary here, and then you can read. And then thank you very much for your attention. Sorry for.
Ya, baik ya. Ini cukup banyak ini pertanyaannya, tapi kayaknya sebagian sudah dijawab. Tapi nggak apa, kita mulai dari ini aja. Ini pertanyaan pertama dari Hesky ya. Ditunjukkan bahwa interaksi alfa melemah pada saat jarak kurang dari 1 femtometer. Kemudian menguat menjadi non-perturbatif regime. Setelah melewati batas itu, bagaimana interaksi itu mengecil dengan bertambahnya jarak. Ini kalau Parada bisa buka chat, sebenarnya dijawab oleh Zulkaida nih. Gitu loh. Nah, kira-kira ada yang mau ditambahkan nggak dari jawabannya Zulkaida?
Tar, saya nggak bisa lihat. Tar, ini kenapa?
Buka chat dulu aja. Di bawah itu ada tab.
Iya.
Itu pukul 11.
Mungkin Pak Aryo bisa bantu summary-nya.
Itu kalau dari Zulkaida dijawab bahwa alfa selalu mengecil seiring dengan mengecilnya jarak. Karena alfa kecil, maka quark seperti bebas tanpa interaksi. Tapi konsep ini disebut asymptotic freedom. Nah, tapi kalau kita bicara di tingkat inti nuklir, kita bisa menggunakan potensial yang bukan asymptotic freedom seperti alfa. Seperti juga potensial. Itu beda lagi. Itu ada yang mau ditambahin nggak?
Iya, mungkin ya hampir sama begitu ya. Jadi ketika alfanya mengecil, berarti kan alfa mengecil bahwa interaksi antara quark semakin melemah. Ya.
Alfa itu kopling.
Ya, di kopling itu ditunjukkan oleh kopling interaksi quark dan quark. Di koplingnya semakin lemah, maka ya ini lambda alfa itu sebenarnya sebanding dengan kopling konstan.
Ini lagi pertanyaan dari Adizul, mohon untuk penjelasan lebih lanjut sebenarnya konsep color pada quark seperti apa ya? Atau kenapa kita perlu konsep color? Ini juga dijawab
karena kalau kita butuh color karena quark, kalau kita tidak bisa membedakan antara quark, misalnya quark dan anti quark, misalnya quark up down quark and between the same quark, right? Misalnya UU quark, right? Yeah, color. The flavor is up and down quark and strain quark, right? That's we call it flavor. Flavor quark is up down. Color, that's what. Kalau kamu mau bedakan quark, the same quark, you need color, like a color red or up quark color red and up quark color blue, for example, right? So you have to differentiate both of these. That's why you did color.
Jadi ini ada apa? Ada jawabannya kalau dari Zulkaida, ada partikel yang punya dan dibuat dari quark yang identik gitu. Tapi
Iya, quark yang identik kan nggak bisa tidak bisa
melanggar Pauli principle karena quark itu fermion. Nah, terus ini dari Hesky.
Enggak.
Ya kan kalau ada dua quark identik kan dia fermion kan tidak boleh ada pada kalian kuantum yang sama.
Oke. Iya.
Ini ada pertanyaan dari Hesky, apa asal dari asymptotic freedom, tapi ini katanya berat ini. Karena tahu saya sih itu belum ada alasan yang itu ya.
Ya itu masih questionable juga ya.
Secara eksperimen dia mati, tetapi secara teori maka dari itu. Jadi ada komentar tentang ini origin dari asymptotic freedom selain eksperimen ya. Secara teori ini ada komentar nggak?
Secara teori sih kita cuma saat ini sih ya. I think we like to experiment anyway, ya.
Belum ada penjelasan berarti ya.
Iya.
Oke, ini ada pertanyaan dari Jafar Asri. Kenapa pi meson masanya sangat kecil? Gitu loh. Sementara kalau lihat dari masa konstituen quark sekitar 350. Gitu.
Gimana?
Kenapa masa pi meson sangat kecil, kira-kira 135, 140? Tapi kalau lihat dari masa quark penyusunnya sekitar 350. Gitu. Kenapa?
Oh, masa.
Ini jawab juga Mas. Ya.
Enggak kelihatan.
Bisa di scroll Pak di chatnya.
Ya, ada di bawah lagi. Oh.
Itu yang mana?
Dari
Itu,
Jafar Arifi.
Ya, Jafar Arifi jam 11.28. 11.28 WIB ya, nggak tahu kalau misalnya boleh.
Apa pertanyaan tadi?
Kenapa pi meson masanya sangat kecil 140 MeV? Adalah kalau kita lihat dari masa quark yang menyusun pion itu harusnya sekitar 350 gitu.
Enggak, itu ke masanya ke penyusunnya kan itu konstituen quarknya 350. Iya 350. Iya. Itu ya good questions anyway. Kira-kira kenapa ya? Good question. I can answer it now. Kira-kira kenapa?
Jadi katanya sih karena emang coba model lama itu katanya. Atau kalau dulu sih jawabannya itu adalah itu modelnya memang masa real 140, tapi konstituen quark model sendiri dipertanyakan gitu. Dia menggunakan effective mass bukan masa fisiknya gitu. Interaksi karena quark-gluon yang complicated dirangkum dalam masa efektif konstituen quark. Memang praktis ya masa quark jam 11.32 AM, 11.32 WIB. Oh, sama Korea beda 2 jam ya kalau nggak salah ya?
Aku nggak. Iya. Aku nggak bisa scroll.
Di chat nggak bisa ya? Sebelah kanan. Nah, ini tanya Ridwan menarik tapi itu. Nah ini coba nih, ini yang dari Jafar Arifi lagi ya. apakah analisisnya bisa diperluas ke eta atau PHI ya, P meson, karena ada quark strange-nya di situ. Lalu bagaimana dengan mempelajari chiral symmetry restoration dengan model ini? Ini kelas berat ya.
Aku nggak bisa gerak.
Di sekolah nggak bisa, 1145.
Iya, nggak bisa nyekrol. Kayaknya ada something.
Biasanya terlihat di sebelah kanan, Pak, panel
sebelah
scroll barnya itu bisa kita naik turunkan.
Ini kursornya
Iya,
ke layar
udah.
utama dulu, terus klik chat buat ditampilkan, terus di sebelah kanan tuh di scroll.
Pertanyaannya tadi si Jafar itu ya, apakah analisis bisa diekstensi ke eta meson, eta atau pi meson?
Pi PHI, bukan P.
Iya, pi meson, right? Iya, bisa, ya. Tekniknya sama aja, seperti baryon juga sama aja.
Komposisinya. Lalu apakah bisa mempelajari chiral symmetry restoration dengan model ini?
Kalau chiral restoration kamu ya bisa aja, bisa. Tapi untuk string quark itu agak aneh, agak karena string quark itu nggak sama seperti up quark. Kalau mau pelajari symmetry restoration, misalnya include the magnetic field or temperature effect kan, if possible, but still questioning anyway.
Anehnya tuh gimana bedanya sama US itu?
Up quark, kalau up quark kan kayak misal tadi saya tunjukkan kan dynamical itunya dari chiral limit itu bisa ini apa dynamics jadi ke effective mass, right? Jadi interaksi antara dengan itu membentuk effective mass. Kalau yang string quark itu agak susah karena massnya diperkirakan nggak sama seperti ini seperti sebenarnya kalau seperti up quark.
Masanya lebih berat gitu.
Lamanya lebih berat, ya, masanya lebih berat di awalnya. So agak susah melihat itunya. Tapi itu orang juga interesting sekarang gitu loh, karena bagaimana kita mengikutkan string quark, charm quark misalnya, dan bottom quark kan. Bisa dipahami, bisa diituin juga.
Itu mass scale-nya beda sekali loh.
Beda. Kalau ya beda untuk charm heavy quark kan, untuk heavy quark.
Ya kalau charm sama B itu hitungannya udah heavy ya, sekitar 1,1 sekitar 4,5.
Ya makanya itunya rule-nya simetrinya juga beda kan?
Rule-nya beda dan juga beda generasi kan, udah beda generasi.
Iya, beda generasi ya, benar.
Oke. Apalagi
Dan itu bisa, dan itu interesting tuh kalau sampai sekarang memang masih banyak pertanyaan untuk itu, untuk yang string quark, charm quark, misalnya kalau include ya, kalau di-include.
Ini ada pertanyaan apa lagi ya? Kayaknya nggak ada lagi. Tapi ini ada isu yang saya angkat aja, jadi kelihatannya nggak untuk dibahas ya, tapi mungkin dibawa pulang aja bagi yang tertarik. Yakni, jadi dalam fisika zat padat ya, itu kan ada perhitungan energi band, kita energi dari elektron dalam kristal. Nah, ini pertanyaannya adalah untuk kristal yang monoatomik ya, yang terdiri dari monoelemen satu unsur, lalu unsur itu inti nuklenya itu diganti dengan isotop yang berbeda. Tapi berbeda, jadi secara kestabilan juga isotop yang stabil secara inti tidak mengalami penurunan, tetapi ada satu nomor massa berbeda, nomor massanya berubah, jadi ada satu ekstra neutron.
Oke.
Nah, ini ternyata eksperimen menunjukkan terjadi pergeseran pita energi. Jadi yang diubah intinya, isotopnya, tapi energi band dari elektron terpengaruh. Nah ini ternyata isunya menarik ini karena kelihatannya tidak ada, betul memang menambah neutron pasti berpengaruh pada distribusi, pada distribusi muatan dalam inti, karena neutron meskipun total mass-nya 0 tapi punya charge distribution, tapi seberapa besar dan juga momen magnetik ini, tapi bagaimana itu mempengaruhi pita energi elektron, nah itu katanya open problem ini. Open problem katanya.
Pita energi elektron.
Iya, energi band.
Oh.
Katanya ini open problem ini. Ini juga saya ingat Firwan pernah tanya ke saya.
Really? Okay. I see.
Ya saya penasaran aja kalau itu bisa dihitung dengan Bethe-Salpeter equation atau enggak. Harus dihitung ulang karena BSI itu BSI ini bisa dipakai juga buat ngitung renormalized band structure kalau di condensed matter yang many particle problem.
Berarti terus interaksinya apa aja? Interaksi dengan inti juga dihitung?
Iya, tapi dalam hal ini saya nggak terlalu paham ya kalau yang kasus kayak gini. Saya juga nggak ngerti. Ini ada eksperimennya aja, cuman dia citation-nya kecil. Nggak tahu apakah karena nggak menarik atau emang susah reproduce. Nah, cuman masalahnya ini sempat ada kolega yang nanya-nanya ke saya. Dia bilang dia menggunakan material lain bisa juga membuktikan mendapatkan hasil serupa, tapi itu unpublished sampai sekarang. Kita belum tahu mekanisme yang benar.
Oke.
Ya barangkali ada ide.
Karbon 13.
Sebenarnya kan kalau Bethe-Salpeter ini sama dengan RPA sebenarnya, random phase approximation.
Betul.
Jadi
ya,
RPA itu kan di condensed matter, iya. Jadi di condensed matter itu dipakai juga sebenarnya.
Memang ya.
Ini paper eksperimen ya?
Ya kalau itu paper eksperimen, tapi penjelasan teorinya nggak memuaskan. Mereka di situ
belum ada ya.
Ya lihat-lihat interpretasinya agak-agak ngawang-ngawang lah.
Enggak, tapi lucu juga ya kalau bisa ditambah proton, ditambah satu neutron misalnya. Iya, neutron ditambahkan, masa elektron band juga berubah.
Iya, itu ordernya kalau menurut paper barusan sekitar 1% perubahannya. Belasan, hampir 20-an mileelektron volt.
1%
dengan band
sih,
gap
1% berarti nggak gede.
Besar itu, Pak.
Spekulatif.
Besar.
Oh iya.
Kalau di feeling kami itu besar.
Less than 10%.
1%, tapi itu di feeling kami itu besar karena mileelektron volt, Pak. Kalau perubahan band gap mileelektron volt itu lumayan.
Lumayan ya. Biasanya kita kalau misalnya less than 10% itu di-ignore aja.
Tapi ini open problem yang menarik kalau saya lihat terus terang sih. Gitu. Berarti kan kalau mau dihitung ulang kan berarti harus suku atau term interaksi elektron sama inti harus diubah gitu kan? Gitu loh.
Enggak, harus ditambah nukleon elektron.
Ya, sementara kalau kita pakai pendekatan yang konvensional ya di condensed matter, kalau ngitung band structure, misal pakai density functional theory, kita nganggap itu pseudo potensialnya tuh masih sama-sama aja sebetulnya. Walaupun ya bolehlah diasumsikan berubah potensialnya, cuman kayaknya sih nggak ngaruh gitu. Dari sisi pseudo potensial yang core electrons dengan elektrons yang luar, terus antara inti juga dan elektron-elektron. Nah, tapi kita sering nganggap itu nggak berubah, dan kita cuma mengganti masanya aja, kita cek hitungan band structure-nya nggak berubah sama sekali.
Iya kan yang berpengaruh massa ya, massa efektif. Kalau
iya, tapi nggak berubah ternyata kalau dihitungan, kalau kita cuma mengganti masanya aja. Electronic structure-nya nggak akan berubah sama sekali gitu. Jadi kita nggak ngerti ini mekanisme yang tepatnya, belum ngerti lah sampai saat ini. Saya ada sempat ide-ide yang lain, cuma saya masih bingung juga. Siapa tahu ada. ada
ini Word Zoom meeting sendiri nggak terpisah buat bicara?
ya kapan-kapan ya. Ini coba kontak-kontak dulu deh, cari-cari ide ntar.
Ya, usul ada Zoom meeting tentang ini ya. Misalkan orang-orang partikel itu jelasin apa aja fenomena-fenomena yang menarik gitu. Dan sering kan muncul misalkan Dirac elektron atau kemudian Weil fermion itu kan udah ditemukan di condensed matter. Nah, pasti banyak fenomena-fenomena yang belum ditemukan. Fenomena-fenomena yang belum ditemukan.
Bukan, HSK bukan. Itu kebanyakan sekarang karena orang bekerja di temperatur effect sama magnetic effect kan. Jadi fenomenanya hampir sama dengan condensed matter. Jadi itu ya Dirac fermion, terus itu chiral magnetic effect, kan macam-macam gitu.
Ya intinya
itu juga hal
gimana kita explore, gimana orang CM itu misalkan dapat inspirasi, misalkan ya sama juga dulu orang partikel juga dapat inspirasi dari BCS misalkan untuk menemukan teori yang lain. Kita juga ingin dapat inspirasi apa aja sih fenomena yang menarik yang belum dirambah gitu orang CM gitu sih.
Tapi sekarang itu yang menarik gini, yang menarik itu yang phase diagram QCD. Which is itu temperatur sama momen sama density. Dan itu banyak orang ini lihat dari condensed matter sebenarnya, fenomena condensed matter.
Menariknya di mana ya?
Yang menariknya itu tadi yang efek magnetic effect misalnya itu kemasnya.
Soalnya kalau di phase diagram QCD itu kan kayak ada kayak magnetik tapi dengan interaksi QCD gitu, bukan dengan interaksi elektromagnetik. Apa istilahnya apa?
Enggak, kan ada phase transition Mas. Jadi misalnya first phase transition itu kan dari quark di confinement ke confinement, which is hadron ya kan, yang misal low density tapi low temperature.
Sekarang ke high
itu jadi kalau pergi ke heavy ion collision misalnya kayak Edison, itu kan high temperature low density. High temperature low density. Makanya kita makanya sekarang kita mau pergi ke arah mana nih? Mau pergi ke arah yang condensed matter misalnya kayak neutron star. Itu neutron star ke high density.
Cold temperature. Temperaturnya cold gitu. Neutron star kan cold ya kan? Neutron star itu cold.
Iya, maksudnya tapi kan high density, itu high density sama temperature. Ya, high density itu dua hal yang tergantung direction yang mana gitu loh, mau kita amati karena ada phase transition di setiap regime. Yang di high density dari itu second phase transition, yang di itu ada first transition, right? Yang sekarang orang happy ion mau.
Kalau saya sih bukan lihat dari segi itu ya kalau coba lihat analoginya itu kan kita bicara dari segi energi density sama temperature. Saya lihat gini, kalau di elektromagnetik kan ada muatan positif negatif, terus ada foton sebagai mediator. Nah, tapi kalau di quark-gluon plasma itu ada quark charge-nya, nah berarti QCD charge ya, bukan elektromagnetic charge, sama gluonnya yang jadi analog foton, dan itu lebih kompleks daripada, jadi ada plasma elektromagnetik, ada plasma quark-gluon. Tapi kalau plasma elektromagnetik kan cuma muatan listrik, positif, negatif sama foton udah. Nah, tapi kalau di ini ada muatan QCD dan quark sendiri ada color charge dan ada gluonnya, dan itu lebih kompleks daripada ya gluonnya kan ada 8 kan, kalau nggak salah gluon itu ada 8. Ada colornya juga, kemudian quarknya ada charge-nya juga, ada QCD charge. Nah itu jadi yang disebut magnetik itu bukan magnetik elektromagnetik, tapi magnetik yang menggunakan color charge dan color gauge field-nya, bukan menggunakan electric charge atau electric gauge field gitu.
Ya bisa juga ada yang namanya itu internal magnetic namanya, internal intrinsic magnetic properties, ya kan? Jadi ada yang
bukan magnetik dalam konteks kita melihat magnetik secara elektrik, bukan, tapi kayak magnetik.
No.
Apa maksudnya magnetik secara elektrik?
Itu kalau misalnya quark-gluon itu di dalam quark itu sendiri punya ini kan, punya charge kan. Charge-nya itu kan ada yang apa? Ada yang kalau dia ada charge berarti kan ada medan,
kita
ada medannya.
Charge elektrik atau color itu dulu.
Ini tetap yuan lah kalau
Quark
itu memang punya charge sama.
Betul. Tapi kalau dalam ini kita membicarakan charge elektrik atau charge color itu dulu.
Kalau
maksudnya
ngomong magnetik ya
charge color itu beda. Iya.
Ngomong magnetik ya yuan.
Benar. Kalau bicarakan momen magnetik nukleon atau hadron, dan di mana momen magnetik adalah momen magnetik dari listrik magnet yang kita kenal, kita tentu menggunakan electric charge dari quark. Tuh.
Iya, terus
Tapi ada electric charge dari
istilah magnetik elektrik itu emang dari punya yuan gitu loh. Kenapa? Sekarang lu campur sama quark, sama apa? Agak SU3 charge, color, udah beda.
Betul, makanya saya nanya itu dari electric charge atau kita bicara color charge, karena ada analogi sekarang kayak quark-gluon plasma, yaitu quark-gluon plasma adalah plasma yang terdiri yang jadi elemen plasmanya itu adalah color charge dan color field, bukan electric charge dan electric field gitu loh. Nah, makanya kalau fenomena magnetik ini dalam quark-gluon plasma, apakah memang magnetik yang kita kenal dari U1 atau analogi, saya bilang analogi ya, analogi magnetik yang ada di color field. Tuh.
Analogi magnetik color field itu maksudnya gimana sih?
Gimana?
Analogi
ya kan,
dari
karena kan kalau electric charge ada electric field. Ada electric charge, ada color charge.
Ya, terus?
Kan? Terus kalau untuk di plasma ya pasti plasma terdiri dari electric charge dan electric field-nya kan. Itu kalau elektromagnetik plasma. Jadi
kalau di yuan ada electric field ada magnetic field. Makanya mereka bisa sebut electric magnetic. Kalau di gates di color mereka sebutnya ya gluon situ, gluon color.
Iya, color charge.
Dianalogikan ininya gluon itu lebih banyak komponennya gitu loh.
Iya,
jadi
banyak komponen.
Kamu mau ngambil yang mana itu sebagai yang kamu maksud magnetik itu apa definisinya? Kan nggak jelas. Ntar kalau ada gates group yang lebih besar, kamu tetap ngambil magnetiknya yang mana? Loh, emang bukan gates simetriknya udah lebih besar lagi. Orang nggak manggil lagi elektrik. Kalau gitu sama pertanyaan elektrik dari SU3 gates itu yang mana? Kan pertanyaannya nggak relevan gitu. Maksudnya beda gates.
Bukan gates-nya beda jelas. Tapi kan ini kalau elektromagnetik plasma itu kan hanya ada 2 muatan ya, plus minus atau satu muatan dan 1 gate boson. Sekarang kalau dalam QCD plasma ya ada berapa muatan tuh? 8 ya. Ada sekian banyak macam muatan dan sekian banyak macam gluon gitu loh.
Ya,
jadi, nah itu berarti tentu struktur plasmanya akan lebih kompleks daripada.
Ya, karena Parada bilang juga karena quark itu juga dia berinteraksi dengan yuan elektromagnetik. Jadi ya quark ini campuran, ada quark dari yuan, quark dari SU3.
Ya.
Ya memang nggak relevan kamu sebut mana yang magnetik dari SU3. Sama juga dengan pertanyaan mana yang elektrik dari SU3. Mana yang magnetik dari SU3. Nggak relevan di situ.
Sekarang kita mau bicara.
Dan itu nggak bisa dibedakan sebenarnya. Nggak
bisa dibedakan, gimana caranya? Ya, itu kan penamaan karena memang dia yuan gitu loh. Kecuali kalau U3 mungkin bisa diambil satu komponen yang dia itu diagonal. Itu mungkin jadi yuannya, istilahnya disebut sebagai charge-nya. Tapi ini kan SU3 udah.
Ya.
Parada, saya mau nanya ini sebenarnya. NGL
NGL
model itu kalau dari pemahaman saya presentasinya seperti untuk menjelaskan meson ya. Hadronnya cuma meson ya.
Enggak meson, semua baryon juga bisa.
Baryon juga bisa.
Cam baryon ya. Semua itu bisa.
Begitu.
Cuma kalau dia mau lebih berat ke cam baryon, kita harus introduce extended ke heavy quark symmetry.
Oh, interaksinya ditambah gitu yang di Lagrange
Iya,
itu.
ditambah aja. Kan itu kan bisa ditambah interaksi. Tergantung
gitu.
apa yang mau kita bahas gitu.
Oh, enggak, ini kan yang low energy efektif dari QCD itu kan sebenarnya banyak ya. Nah, salah satunya kan yang ya nggak tahu deh seberapa rame juga yang saya kerjakan tentang scheme model.
Nah, scheme model ya.
Nah, ini kalau dibandingkan dengan NGL, apa sih keuntungan dan kekurangan?
Hampir sama sebenarnya. Cuma bedanya kalau scheme model dia kan lebih ke soliton ya.
Ya, dia jadi kok fundamental.
Jadi soliton. Bedanya gini, kalau di NGL itu kan kita langsung quark.
Iya.
Kalau di scheme model itu soliton sama ikan apalagi pion field.
Iya.
Tapi NGL bisa dibuat jadi soliton kalau kita bosonize. Jadi quark-gluonnya di bosonize jadi soliton, terus yang itunya jadi quarknya jadi pion.
Oh gitu.
Jadi bisa. Jadi ada itu kita lagi ngerjain juga itu yang tadi aku bilang non local chiral quark model. Itu juga itu based on the scheme model.
Oh.
Iya.
Karena seingat saya kalau scheme itu dia fundamental field-nya itu bukan quark seperti NGL model.
Bukan. Iya, bukan.
Dia
soliton
lebih
sama
meson.
Pion field.
Ya, jadi fundamental field-nya adalah meson, sedangkan baryon sendiri itu adalah topological soliton dari modelnya scheme itu sendiri.
Tapi kan baryon diambil dari baryon number.
Itu di scheme model didefinisiin. Ini secara klasik saja definisiin sebagai topological charge. Karena soliton kan punya topological charge.
Jadi topological charge equal 1 ya.
Iya. Wah, bisa lebih, cuman permasalahannya dia dengan eksperimen belum cocok untuk higher baryon number. Itu yang
untuk hyperon juga agak susah kan?
Selain proton dan neutron, dia seingat saya susah.
Agak susah.
Kalau baryon number equal 1 dia masih
oke ya.
Fit 30% lah.
Iya, itu yang aku baca juga dari Manton ya. Kan kemarin dia kasih kalau kamu dari Cambridge dia di Oxford apa Cambridge. Dia kasih talk, dia bilang begitu. Jadi kalau misalnya topological charge equal 1, baryon number equal 1, scheme model masih oke. Tapi kalau untuk pergi ke baryon number larger than 1, misalnya like 2, 3, 4 gitu, itu agak masih susah.
Enggak, saya menarik yang kamu bilang bahwa NGL itu juga bisa ini kan baryon. Padahal scheme model sendiri dia fundamentalnya hanya meson.
Gimana?
Maksudnya NGL itu kan dia start dari quarks ya, quarks. Fundamental field-nya kan quarks kan. Nah, ada nggak maksudnya formula jadi sepertinya di NGL ini di higher end lebih energi lebih tinggi daripada skemion ya kalau scheme model ya kalau saya lihat. Ada nggak dia itu bisa scheme model diturunkan dari NGL model atau apa? Ada nggak kamu baca?
Iya bisa. Itu tadi yang aku bilang itu dari kalau misalnya NGL model di bosonize pakai bosonization, nanti kamu dapat hampir sama dengan soliton atau itu scheme model.
Model scheme. Oke.
Iya.
Oke. Very interesting. Oke, thank you.
Ya.
Oke,
sudah. Apakah masih ada pertanyaan yang lain karena kita sudah pukul 12.18 ini.
Dari YouTube sama FB sudah sih, Pak.
Sudah semuanya, nggak ada lagi.
Sudah ya.
Ya sudah, baik ya. Going once, going twice. Oke, kalau tidak ada, baik. Terima kasih atas presentasi dari Dr. Parada ya, sangat menarik dan menambah wawasan kita semua seputar perkembangan terkini dari fisika teori partikel elemental, terutama struktur hadron dan bagi yang ingin tetap diikuti ya seminar Kolokium Fisika daring dari Fisika LIPI setiap hari Selasa pada pukul 10.30 hingga pukul 12 WIB. Terima kasih sebesar-besarnya kepada Dr. Parada ya yang sudah meluangkan waktunya berbagi ilmu, dan sampai jumpa di kolokium berikutnya. Tetap semangat, selamat beristirahat siang bagi waktu IJ dan di negara bagian lain. Demikian kami akan akhiri meeting ini. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Mantap, mantap. Terima
Oke,
kasih
terima
semuanya. Ya.
Terima kasih
Pak
semua.
Zulkaida,
Ya.
terima kasih sudah menjawab beberapa pertanyaan melalui chat. Padahal tadi langsung aja ini pakai audio juga nggak apa-apa. Oke, makasih ya Pak Parada.
Oke, makasih ya.
Terima kasih banyak. Ya,
Pak
ini
Ridwan.
kita end meeting sekarang ya.
Oke, ya. Oke, thank you.